Okay, so as I said previously, it is possible to have and talk about a fractal dimension in the time domain. So let's look at what we mean by that. To talk about dimensionality in the time domain, you need two scaling factors, one for time and one for magnitude. So if you look, our new equation for dimensionality is going to contain both of those features. So the time scaling y has this t over a parameter, and then the magnitude scaling is this a to the power alpha. So time is scaled and magnitude is scaled. The reason you have to have this is that you need, because you have different dimensions, because time is a different physical feature than whatever the function of time is that you're measuring. So unlike space, we have an x dimension and y dimension, and they both represent space. Here we have time and some other physical feature. So we have a scaling parameter in both time and in magnitude. So the self-similarity parameter, this alpha, is by definition the self-similarity parameter. So here's a physical picture of what we mean. Here's a time signal, and then we choose some subset of this time signal and expand it. And you can see that if we look at our signal y, and then our signal some magnitude or some scaling factor m times y, where we have magnified this in the time domain. So we have both a magnitude factor in the y dimension as well as the scaling factor in the time domain. And this mx represents how much magnification we got in the time domain. My represents how much we scaled the y domain. And if you look, you see that the signals look similar. And so if we were to take a subset of this signal and magnify it as well, we would get another signal that looks similar to these two. And so that's what we mean by self-similarity across scales. If we take the probability density function and we look at this window in sub I, or in 1, sorry, if we look at window in 1, we see that we get the following distribution function. And then if we look at in 2, we get this narrower distribution function. If we now look at the standard deviations, or sorry, the variance, if we look at the variances here, and we plot the log of the variances over the log of the window length, we find that we get a slope here, and that slope is actually going to be alpha, our self-similarity factor. So this alpha is a parameter that can be used to get a feature from nonlinear or chaotic signals. So it can actually be used in a pattern recognition system as a feature. So once again, the self-similarity parameter can be defined as the relationship between the magnification on the time scale and the magnification on the magnitude scale. And we can actually get an estimate of magnification in time and magnitude from the standard deviations of the two distributions. So that was what was physically illustrated on the previous slide. So in a practical application, how would you calculate alpha? So we've got a data set. So what you want to do is you want to choose several window segment lengths using the same temporal magnification. And for each of the windows, we'll find the standard deviation and take an average. Using the standard deviation, the average standard deviation, for the temporal magnification rate, we're going to determine alpha. And then we're going to repeat this for different magnification factors in the time domain. We're going to plot S versus N and fit the standard deviation versus N, and we're going to fit the curve to best determine the similarity ratio parameter. So The fluctuations of a fractal signal are going to increase as the time record length increases by a power law relationship. And so true fractals have unbounded size in both dimensions. But biomedical signals are thought of as unbounded in the time domain, but due to physical limits, they're bounded in the magnitude domain. So the question is, how do we obtain an unbounded signal in the magnitude domain, and why is it important? So we'll look at the figure on the next page. It's going to illustrate a random signal. Two cases. One is a random signal and one is a self-similar signal for the time between heartbeats taken over a 24-hour period. So let's look real briefly. Okay, here's our random signal. Here's our original data set. So both signals can be expanded in the time domain for a representation of self-similarity, and they result in a magnitude magnification of 1. So from the equation, this would give a self-similarity parameter of 0. So the physically significant data and the uncorrelated random data have the same result. So that's why it's important to figure out how to get an unbounded signal. Excuse me. So once again, you can see these two data sets are very different, but if we were going to try to use this self-similarity parameter as a feature, we get the same thing here. So clearly that's not going to work. So what we want to do is we want to take an unbounded signal. And the way to do that is to take the time integral before the magnification is done. This is going to result in a difference in alpha for the two previous signals shown. So basically, you let the data set be represented by some time series x, and you have an average value, x average, which is represented by x in the triangular brackets here. So the first thing you want to do is you want to subtract the average from the data, and then we're going to integrate the time series to obtain an unbounded function. This is called the cumulative sum. Now, let's go to the next slide. The next thing we're going to do is we're going to take our unbounded function y, and we're going to divide it into a series of boxes of length n. And then for each box, we want to do a least square error fit to get the slope and intercept of a line that best fits the points in the box. Then we're going to subtract that line, ai plus b. We're going to subtract that line from the unbounded function and find the mean square error, or find the square error. So here are our boxes. Here's our original data. Here is our best fit line. Okay, and we've divided this into boxes, getting a best fit line for each box. This is called local detrending. So what we're going to do is, for various box lengths, we're going to do local detrending of the data. So once you have A and B for a given box, you can detrend the data by subtracting the trend line. And then you get the fluctuations of the curve from the trend. So here is our effectively our like an RMS value of what remains after the trend line is subtracted. Now, as n increases, your mean square error should increase. Now, we're going to repeat this calculation for all possible box sizes, and then we're going to plot f of n versus n on a log-log scale. And the slope of this line is basically the self-similarity pattern that we previously discussed. So physically, if this self-similarity pattern yields a value alpha that's less than 1/2, the data are anti-correlated. If it is equal to 1/2, the data are uncorrelated and we have white noise. If it is greater than 1/2, the data are correlated. If alpha is equal to 1, we have what is referred to as pink noise or 1/f noise. If alpha is greater than 1, we have a non-stationary sort of random walk unbounded signal, and if alpha is equal to 3/2, we have Brownian noise. So here are some examples of those. White noise would be a random signal. It would have a flat power spectral density. The signal's power spectral density has equal power in any band at any frequency, and it's analogous to just a white light that would contain all frequencies. Pink noise is a process with a frequency spectrum, and in this case, the power spectral density is proportional to the reciprocal of frequency. It has a 1 over F relationship. Pink noise has an equal amount of energy per octave. It's somewhere in between white noise and what is referred to as red noise or Brownian motion. And then in red noise or Brownian noise in science represents Brownian motion, and the actual name comes from Robert Brown, who was the discoverer of Brownian motion. So let's look at a couple of applications of looking at the fractal dimension or the self-similarity dimension for different biomedical signals. So the first thing to look at is human heartbeat. So in this case, what people were looking at was the distance, the time between beats. And so a detrended fluctuation analysis or a DFA analysis was done on a healthy subject and a randomized control. And so we see that one subject yielded an alpha of 1.04, another of 0.51. Looking at the spectral analysis, our randomized control signal is just a flat line. It's just a stochastic type signal exhibiting white noise. Our spectral analysis exhibits this 1 over F type behavior. So the difference between just a randomized signal and an actual person looks like this. So the human heartbeat, yes, it is fractal because it has a dimensionality, or it has a 1 over F behavior, and it has a scaling factor that is equal to approximately 1. So now let's look at what happens as you have different situations in the heart rate signal variation. So this figure shows the results of a study where a healthy young person was compared with a person who was healthy and older, and compared with a person who was in heart failure. So the slopes, it's not totally obvious, but the slopes here of the log-log plot, the person in heart failure has a slope of 0.5. The healthy young person has a slope of 1. The healthy elderly person has a slope of 1.5. And so you can see that as you get older, your fractal scale changes. Your fractal scale also changes if you have heart failure. Another common application is the analysis of human gait patterns. So here's an example of a person walking, and what's being measured is the stride interval. In other words, between steps, here to here, what is the time between steps? So if you plot stride interval versus time, you find that you get fluctuations. And so the question is, okay, so we have these fluctuations. Are these fluctuations a random stochastic process, or do they have some fractal dimension embedded? So looking at these fluctuations in a walking rhythm, it's very analogous to the cardiac heartbeat, but at one time people thought, like the heartbeat, that it was very regular under healthy conditions. But when measured, you see that you do see some fairly complex fluctuations. And so people thought this was just kind of a random stochastic fluctuation, and then began to look at sort of a chaos fractal analysis of this gait pattern. So the simplest explanation is that these would represent some kind of uncorrelated white noise that's superimposed on a regular process. So in other words, you've got a normal constant walking rhythm, and then you superimpose white noise on that. Another possibility is that maybe there's some kind of short range correlation, like something in a Markov process or where there's exponential decay of the system. In that case, the current value of the stride interval would be influenced only by the most recent stride intervals, but over the long term, fluctuations would vary randomly. And then finally, a third possibility is that the fluctuations have long-range correlations of the same type that you see in a healthy human heartbeat, as well as other sort of fractal phenomenon. If this are the case, the stride at any instant would depend on the intervals at remote times, and this dependence would decay in a power law fashion. Okay, so what we're really saying is that there's some memory in the system, and this contributes to the fractal nature of the signal. So the first thing to do is to calculate f of n versus n to determine the self-similarity pattern for a data record of gait. And the next thing to do is shuffle the data. So you've got these windowed segments of the data, and what you're going to do is you're going to randomize the order of the window. Now this is not going to affect any statistical parameters, but it would have an effect on any hidden long-range order in the signal. So here's a 9-minute walk, and here's our original data. And then here are shuffle data. So we've basically taken this data set, divided it into windows, and shuffled the order. Then when we do a detrended fluctuation analysis, we find that for our original data, we get an alpha of 0.83. For our shuffle data, we get an alpha of 0.5. And then the power spectrum does illustrate a 1 over f kind of behavior with a slope of minus 0.92. In this particular data set, walking speeds were varied to determine whether pace affected long-range order. And the result was that both the fractal and the 1 over f behavior were preserved for thousands of steps at various paces. So slow walking, normal walking, fast walking, and randomly shuffled data. You can see that this detrended fluctuation analysis shows different values of alpha, and then the randomly shuffled data, alpha 0.52. And the 1 over f behavior, actually a little more similar. You get minus 0.98, minus 0.68, minus 0.91, and then random would be a slope of 0. So if you look at how this changes with aging and disease, if you compare young and old, you see that young have an alpha of 0.5, while elderly have an alpha of 1. If you look at individuals with Huntington's disease who are known to have gait variations, you can see that your normal control has a value of 1, while your individuals with Huntington's disease have a value of 0.5. And I'm sorry, over here I was wrong. The normal elderly value of 0.5, young value of 1. So alpha as a feature can actually be used to distinguish individuals with Huntington's disease. The interesting thing about this study is people are looking at this as a predictive or diagnostic tool to determine, can you identify things like Huntington's disease, Parkinson's. A lot of these types of illnesses are difficult to diagnose in the very early stages. So one of the things that seems to be affected early in some of these diseases is the fractal gait pattern. So that's one thing that people are looking at as a feature to identify that. Another thing that's not discussed here in these lecture notes, but that has been used, is this 1 over f behavior. The EEG signal exhibits 1 over f behavior. And people have actually implemented this into a device to monitor anesthesia. It turns out that when an individual undergoing surgery is properly anesthetized, the 1 over F behavior of the EEG is distinctly different than it is when the person is awake and alert. And it's also distinctly different from normal sleep. So there actually are patented devices that monitor the 1 over F of the EEG to indicate when a person is appropriately anesthetized. That's particularly important if you have to be anesthetized for several hours because you don't want too much anesthesia under that circumstance. So anyway, this is just a set of notes that I did a few years ago on fractals in the time domain. I think maybe they add a little bit of clarity to what's in your textbook.